The regeneration of jet engines contributes to a large portion of airline operating costs. The Collaborative Research Centre 871 develops a novel approach that combines improved repair technologies with a virtual rule-based decision-making process. After tens of thousands of hours, a jet engine is removed from the wing and almost completely disassembled. Afterwards, all components are evaluated and damaged parts are repaired or replaced. The novel approach is exemplified here for a turbine blade. As a first step, the turbine blade is disassembled carefully and placed in an intelligent workpiece carrier. This carrier accompanies the blade through the regeneration process and stores all necessary component and process information. With the help of an autonomous transport robot, the blade is guided through the regeneration process. The micro and macro geometry of the blade is measured using an optical multi-scale measurement system in order to detect damage and geometry deviations caused during operation. Afterwards, the blade is inspected with high-frequency induction thermography in order to detect cracks, which can lead to blade failure. The measurement data from the inspections are combined and stored in a virtual twin of the blade. Based on the virtual twin, damage, such as geometry deviations or cracks, is characterized automatically. Depending on the condition of the blade, there may be several possible regeneration paths. These cover the replacement with a new part, the refurbishment with different repair methods, or the reinstallation of the blade without repair. In order to allow the selection of the best possible regeneration path, the performance and remaining lifetime are determined by means of functional simulations. These are carried out for the operationally stressed blade without repair, as well as the expected condition of the blade for each regeneration path and compared with the new blade. Based on this information, the best possible regeneration path is selected, taking into account the customer requirements. The determined process steps for the best regeneration path are stored in the intelligent workpiece carrier. The transport robot uses the information on the intelligent workpiece carrier to bring the blade into the correct process cell for each step of the regeneration. In order to repair the defect at the blade tip, additional material is applied to the tip. Our developed single crystalline laser welding process allows the restoration of the monocrystalline structure of the base material. Subsequently, excess material is removed and the recontouring of the blade tip is performed using a dexterous milling process. The last step is the coating of the blade. With the developed near-net shape hybrid joining and coating technology, the process chain can be significantly shortened. Finally, a quality check is performed. In order to ensure that the repair was successful, it is checked that the repaired blade is within the geometry tolerances and free of cracks. The approach of the Collaborative Research Centre 871 will significantly improve the regeneration process in the future. The amount of new parts and the repair effort can be reduced, and valuable resources are saved.